Hey, hey, YouTube. Ben, we got Ben jumping back in the seat. How you doing today, Ben?
Flustered, but we're doing this. We're doing this.
So you can all see Ben's new digs behind him too. Maybe today we'll get a quick tour. Uh,
Yeah, it's still completely messy and unorganized, but I'm making progress, slow but steady. This is the problem when you're trying to set up a lab, an office, and a recording studio all in one space and still have to work a full-time job. It's
right.
very little additional time, but I'm gritting my teeth and getting through it bit by bit.
Well, you actually just answered my first question. I was going to say, how many different sections of your workspace do you have? And you just said you've got an office, basically an AV area, and an electronics lab, right?
That's it. That's pretty much it. I also have, I went to UCSD surplus sales and got some furniture. I got a couch, a three-seater couch, and a coffee table. So there's going to be a little bit of a chill area.
Right, right.
There's a
Need
kitchenette
those.
as part of the office, and there's also a restroom, which is great. I mean, I could almost live in here, but the rental contract specifically says no overnight lodging is permitted. So if I'm working through the night on a project, that's allowed.
Right, right. Yeah, in my old office, I didn't have that writer, and so I've spent many a night. I even had, because back in the days of Commodore, the running joke was we needed a shower. When I built my own office space, I built a shower right in my office, so I had a personal shower for the, and so I've actually spent the night in my office. I had a DirecTV cable, I mean satellite, because we were in an industrial park where you can't get cable. So I had all the comforts of home, sushi
I, I
delivery, everything.
I could. I'm supposed to be. I'm still. I've been renting this space since 1st of October, so it's been nearly 3 months, and I still haven't had any word from AT&T when they're going to put the fiber in. It's really, really frustrating. I've run all the Cat 6 Ethernet cables. The way this office is constructed, it's part of a group of offices in a bigger building, and different suites are rented out, right? And they had uh, telecommunications conduits in the walls already, even
Right,
though the walls are fully insulated with fiberglass, which is amazing. And so all I had to do was run it up through the cable, run all the cables up through the conduits, and they go across into a box in the restroom where I've routed them all into a punch down, and my Ethernet switch is there. It's all just there, ready to go as soon as AT&T get around to installing a cable. That the problem was there's two halves of this building, and they have a fiber in the other half, and this half they never ran it. And there's Cox in here, but I hate Cox. Cox are
Cox is who you had at the old place at
well,
at your house, right?
problem is they're for the same speed they're about an additional 60% on top the monthly price.
Right,
So I'm not going to do that. In the meantime, I do have free Wi-Fi access, but it's bandwidth limited to about 4 megabits down,
right,
2 megabits up. So if I go fuzzy during our streams, I'm sorry, but that's Cox. That's the
right.
that's the Wi-Fi I have to connect to until AT&T get their act together and give me 100 megabit dual, like sync. It's going to be 100 megabit down and 100 up. Like so,
Symmetrical. Okay.
yeah. So we'll be once that finally gets done, we'll be able to stream beautifully. But I'm still waiting, which is it's super frustrating. But here I am. I'm at my electronics workbench. It's still not perfectly organized. I'm getting the camera down to show you. There's still instruments up on the rack there. There's my scope and soldering ovens there. I've got on one of those Costco metal shelf racks. I've got a bunch of different parts for doing guitar repairs and electronics. And here is some strings of Christmas lights that were no longer working, and I just thought I'd have fun because a few years ago, for some stupid reason, I bought like 4,000 warm white LEDs from China. I guess because they were so dirt cheap, and I got all overexcited while I was on AliExpress and just ordered too many of them. And behind me, you can see is some of my guitar gear, and this is the studio section where I have that workstation is set up for video and audio recording and editing, and those are acoustic screens with a drapes in front of them. So I'm trying to get set up to do content creation, and it's been a long journey, and I'm good at a few things and not good at a lot of things, but one of the things that seems to keep coming back around in the work that I do, not so much here at when I'm now at Autodesk, but certainly at Altium, is content creation, and I just can't get past that. That's probably what I should be spending any extra time doing, is content creation. That's why we live stream, right? We want to share what we've learned and talk about interesting things and discover stuff together. So, yeah. Anyway, waffling on, but that's a brief tour. When it's fully set up and cleaned up, I'll actually do a formal tour video, or we can do that as a live stream. But today, it's the season to be jolly, and I have a bunch of Christmas lights that I've already separated out this one string, and the goal was to replace all the old light bulbs with these warm white LEDs. But to do that, we need to do a few things. We need to research these LEDs, in particular, what kind of current we should be putting through them. You can't just hook up LEDs to 120 volts AC. I mean, cheaper brands do kind of do that, but they flicker like heck, and they don't last because at the peak of the wave you're overdriving them almost invariably. So I just thought this could end in complete disaster, or it could be fun. So I don't know. What do you think, Bill?
Well, I liked the word warm when you're talking about white LEDs, and of course by white LEDs, not of course, but I'm assuming that there's multiple LED dye in the package, and they're combining a red, blue, and green to make some kind of white. Is that your impression of these LEDs? Well, because there is no white LED dye, right?
No, there isn't. And there's two ways you get white. One is, as you mentioned, you mix red, white, and green, red, blue, and green together.
Right.
I only said red, white, and blue. I'm feeling.
There you go.
Patriotic. You mix primary colors, green, red, and blue. And that's, of course, that's how dot stars and neopixels work. Is you have three chips in the one package, and a controller IC that does the PWM to change the brightness. These ones are not smart LEDs. They're just dumb. They're single color warm white. And so these do it the old school way. These actually use a blue chip. Now, the blue chips have a fairly broad spectrum. They start in blue visible, but they actually end in ultraviolet. And so they give off a good amount of visible blue light, perhaps even some in the low end of the green spectrum. And then the other end, there's ultraviolet. So what they do is they coat the chip with a phosphor, much like fluorescent.
Phosphor? Okay.
Yeah. So what they do is they coat the chip with a phosphor that generates amber or yellow or some broad spectrum from yellow all the way up through to red, and that gets mixed with the blue and the green that comes off of the chip, and together they form white. And the amount of phosphor that they add, or the type of phosphor that they add, can change how warm or how cool the white light is. But so white LEDs are not proper white. They're really blue plus yellow. But but they're broad enough in the spectrums that they overlap and form like good quality ones will actually give you very high, what they call CRI, color rendering index. The closer to 100% you get, the closer you are to natural sunlight.
Right. Yeah, let's talk about color temperature. What do we mean when we say warm, and why is that different than a fluorescent lamp, which come in color temperatures also? What are we really rating them as, or talking about them as?
Well, warm white is anywhere like 3000 K and below.
Right. I was going to say 2300 to 3000. Yeah.
Yeah, but you could have. That's right. You could have a 1800 or 2000 Kelvin color temperature gas discharge lamp, and it's going to look bright orange. That's what they have in car parking lots. Those are really the most efficient lamps for visible light output versus power input are sodium vapor lamps.
High pressure sodium vapor, yeah. Because there's a low pressure version also.
And the low pressure ones used to be used on street lights, and they're the long thin tubes like fluorescent tubes, and they're very orange.
Right.
And so if you take sodium vapor and you put sodium in a glass envelope and you suck all the air out and you vaporize the sodium, that's low pressure sodium vapor. That gives you that orange glow. And when I was in college, actually my college had a really cool, one of the labs had a bunch of these different tubes with slits in them to make a narrow slit of light come out with different gases in the different tubes. And then they had another prism with an eyepiece that would darken everything else around it. It wasn't just a glass prism, but it was a prism inside of an enclosure that was all black inside. So you could just see and really focus on the spectrum, and it had a spectrum gauge inside of it, so you could look at the different things. They had a mercury vapor lamp. Actually, no, that's not correct, because mercury vapor produces short wavelength UV, and they wouldn't have people staring at that. It had cadmium or some other metal vapor that generated visible light. They had some of the noble gases, neon and all those. They had air and they had hydrogen, and then they had sodium vapor as well. So you could see the lines in the spectrum these lights were producing, and the sodium vapor lamp spectrum had two very clear thin lines in the yellow and nothing else. It was like really obvious. So sodium vapor gives you this very clear yellow light and nothing else. So the ones that they use in car parks and on freeways now have a little bit of other stuff mixed in to give it some blue, so they're not pure yellow.
White is yellow, yeah.
Yeah, but yeah, xenon's probably the best for natural white light, but and that was using camera flashes for a long time.
Right, strobe lights.
Super expensive to obtain xenon. It's got such a low liquefying and such low freezing points that it's very, very hard to separate it out from the air. So a little bottle of xenon gas could be like $10,000. Super expensive.
Wow.
Yeah.
So I learned about capacitors the first time I saw the back of a xenon lamp. You can hear I pronounce it differently here. I'm from Indiana, right? But I had opened xenon. So I had opened my dad's strobe light, and there was these cool 3 wires going down to the trigger bulb, to the bulb, right? And of course, a xenon lamp, when it's not in conduction, it's not in conduction. It allows a charge to build up across the terminals, and then you hit it with a 2.5 kV trigger pulse to ionize the gas and create a conductive path until it stops being conductive. Then it's isolated again.
Right,
well, I reached.
It charges those big caps, like they dump all that energy really quick, and they exhaust themselves and can't sustain the arc because amps of current flow in those things. Yeah.
Yeah. And so looking at the back of the xenon bulb, I'm like, oh, look at all those little wires. I stick my finger down in it, and the charge hit my hand and blew my hand back to like this. And I immediately brought my hand back. I looked at it. I went, those big blue things are fast. I'm like 8 at the time, right? I'm like, those big blue things are fast batteries. And I was talking about the capacitors. I had figured out that's what shocked me. And that was my first lesson other than a crystal radio. I think that was the very first thing I had ever made in electronics. And so my dad's strobe light, I never got hit by high voltage after that. I learned my lesson at the age of like 8 to 10, somewhere in that age.
I have a strobe story. I actually
okay.
This is my favorite multimeter of all time, right? It's actually a Metex meter.
Okay.
I bought this meter when I was in my first year of college at the beginning of the year. It was my first ever tax deduction going into a career. It was in 1993 I bought this. It was about 200 Australian dollars, a little over. Branded as Dick Smith Electronics. This is back when Dick Smith was actually an electronics store and not just a consumer products business. I bought this one because it had everything, including capacitance meter, which was not many meters had that at the time, and a transistor HFE measurement. And in the side is this little row of 5 holes. That's an RS-232 port, so it'll do data logging if I hook it up to a serial port. So I bought this from Dick Smith when I was 18. Okay, so if you do the math, you'll find out I just turned last week. I just turned 47, so I'm feeling it. Anyway, what was the whole point? Dick Smith. That's where I used to go buy all my technical books way back when I was learning at the beginning. And Dick Smith also used to sell kits from electronics magazines in Australia. There were a few of them when I was growing up. And one of the kits was a beat triggered strobe light. It was a strobe light, but it also had an audio input jack.
Right.
And you could put it into a mode where it would filter and listen to the low end frequency of a music source. And so you could hook it up at a concert. You could actually hook it up to a send from the mixing console from the snare drum. So the strobe would flash whenever the drummer hit the snare drum. It was really cool.
Right, right.
That was the first really dangerous, complicated thing I built. And I was 11. I got it for my 11th birthday as a kit. And I made so many mistakes. I used a tiny little dinky toggle switch for the main power switch. And
right.
And the big switch, which was, I could tell it was for power, but I couldn't figure out where all the cables had to go in the folded metal enclosure that it came with as part of the kit. I didn't put the Perspex cover on the front to stop people from touching the bulb. All sorts of mistakes I made, but it did work. And I remember before they'd actually done a recall on them, and they sent everyone a letter who'd bought that kit saying, if you have bought this kit, send it in to Dick Smith. We'll pay for the shipping. Our technicians will check your kit and make sure you've constructed it correctly and send it back. Because I think they became terrified that a lot of kids were building it, and it was really dangerous. You know, high discharge, big capacitors inside, a 4 kilovolt trigger transformer for triggering the arc in the bulb, as you'd pointed out. And a lot of areas where people could make mistakes and do it so it wasn't, you know, wired correctly and could get light. Like the whole thing was in a metal enclosure. If someone didn't wire it up correctly, the whole enclosure could go
Enclosure
light.
Could become hot, yeah. With the trigger voltage, no less. Yeah. So
so I sent it in. They sent it back with all the corrections made. So I was really happy. But I remember one day showing it off to a friend of mine. He's like, "Oh, that's really cool," and I'm like, "Yeah, I made this. It was a kit. I soldered all the parts on the board. It works great. And I took the cover off to show them what was inside. And I was pointing out, but I never unplugged it from the outlet.
Right, right.
So I'm like, I just reached in and absent-mindedly, I wasn't intending to touch anything. I said the power comes in here, and my finger just went that little bit too far. And
right.
Boom! Like, flew me right across the room. I didn't get knocked out or anything, but my whole arm was aching all afternoon. So,
yeah. I've had the shakes from catching a good voltage. I've got a story that happened to a friend of mine, Headley Davis, who is known from Amiga and Commodore fandom. Actually, also Xbox. He worked on the DRAMs for the first Xbox. He had a Jacob's ladder, and he went to show it to his friends. And he had a fluorescent, not a fluorescent. He had the step-up transformer for neon bulbs and whatnot. And it didn't start. And he goes, oh, maybe they're not close enough together to strike an arc. And he's like an idiot, I grabbed the two things. And he catches whatever, 14 kV or something like that.
That's a total Electro Boom move right there.
Yeah.
And that's probably my favorite Mehdi Sadagda Electro Boom video, is the one where he is celebrating 1 million views or something and makes a Jacob's ladder out of sparkler sticks. He gets those big long sparklers and bends them in and makes a Jacob's ladder out of them. And at the end, the whole thing tips over and lands on him while it's going. Awesome.
Phosphor burns and whatnot. Yeah. So you mentioned the light activated, or the music activated sound, in this case a strobe light. The very first thing I fixed, I was in 4th grade now, and my dad had got me one of those 150-in-1 kits with the springs, and so I was already into electronics in the 3rd grade. And then, I've got one on the shelf here. We should talk about them someday, maybe drag them out. And in 4th grade then, my dad had won a contest, so he got a little bit of money, he bought a stereo, and he bought what we called a light organ back in the 70s, which is the pulsing... Yeah, and so red and blue
kits for them too.
Right. So red and blue was the bass, and yellow and green was the highs, and they would flicker, and there was a piece of Fresnel plastic in front of it. And the red and blue stopped working, and I troubleshot it to a device that I found out was called an SCR. So they weren't even using thyristors, which are bidirectional, give you both cycles, but an SCR would give you, it was a silicon-controlled rectifier with a turn-on gate. And so it would give you half cycles. So they only ever lit up half brightness, but nobody noticed. And I replaced his SCR. I went to the local TV repair shop, got an ECG replacement, I'm sure. And my dad paid me $4 for it. I'm like, Dad, I don't need your money. He said, you should be paid for your skills. And I'm like, a light bulb went off, right? And so that was probably the start of my electronic career, was fixing my dad's light organ. So I never looked back. I was fixing CBs by the time I was 16, Yeah.
I think thyrist is technically like a class of devices, and under that you have the one-way, which is your SCR, and the two-way, which is your triac, right?
Right. Yeah, and they're thyristors. Right, I call thyristors the triac. Yeah, and then there's diacs, which you can use to trigger the thyristors. If it's a poor man's trigger, but it's it's basically a bidirectional avalanche diode.
Yeah. Yep.
So, now you mentioned flukes, you mentioned handheld meters, and my handheld meter, and I'm panicking because I normally have 2 Fluke 77s that I've had since my 20s. And I lost one, and now I can't find the second one, so I'm panicking. But I just noticed Dave Jones had just put up a video about why is Fluke twice as expensive. And I watched enough of the video. I think it's because it's made in America was his answer to that. But I need to either find my Fluke 77, or I'm going to go through withdrawals, and I'm going to need to get another one off eBay or something. So it's just that was always my go-to Fluke. It's like I knew how sensitive the AC was. I knew I knew the diode checking things by heart. So it's my go-to meter. I'm just very comfortable making measurements. And I used to keep one Fluke when I had both on my shelf here. one would have 2 probes on it and one would have 2 easy hooks on it, so that I'm grabbing the meter without having to change the leads. I'm grabbing the meter based on what I'm measuring with them. And then my Keithley is when I need to be real exact about something.
This is my Fluke.
Yeah, what's the model number on that?
This one's 8010A.
Okay.
So this is really old. It was probably made in the very early 80s, but still reliable. It's got cal seals on it. I'm pretty sure like they're pointless now. Last time it was calibrated was in 2004. I'm tempted to pull it apart to put a backlight on the display because this is probably a first generation LCD display.
Oh, that had probably poor contrast. Yeah.
Well, it's just dark. It's clear when I'm looking straight at it. If the room is well lit, there's no problem. It's just the room is. It's nowhere near as easy to read as some of these others that even have backlights and everything. So.
Right.
Yeah. So I just realized
in my bench,
I was so busy trying to get my lights set up and clear the bench for today that I didn't get out the parts that we're looking at here. At some point, as I try to make this current control LED string, I'm going to be rummaging for components. They're all here, but they're all in different places. But
now, are you going to use the string for anything, or is this just for the bench to play around?
It's just to play around with. If it works well, I'll probably design an actual current drive PCB and put a microcontroller, probably put an ESP8266 module on a board to do PWM, because I've got three different strings, and perhaps I'll make them all white because I have all these millions of white LEDs kicking around, but still have them fading and stuff,
Right. So why series? Why are you looking at put them in series? Just for fun, or is there an electrical reason? Because the trade-off, of course, is the voltage has to go up.
Yeah. Yeah. Well, really, the real reason is that the light strings I have that I'm replacing bulbs with LEDs are already in series. So, and LEDs you don't generally run in parallel. I mean, there's some low-cost LED strings that they run them in parallel, but you're relying on the internal variable resistance of the chip and the lead frame to make sure they all share current evenly and illuminate.
And that doesn't work. That actually, yeah. So let's talk about that. If you put two light bulbs in parallel to each other, they're roughly 2 equal resistances when they light up. And, let's say one ends up to be 40 ohms, the other one 41 ohms. At temperature, they still will almost equally share the current because they look like 2 close resistances of similar value. But an LED, when it has a forward voltage where one at 2.1 volts and one at 2.2 volts, the 2.2 volts will turn on, the 2.1 volt will turn on and steal the current from the 2.2 volt, never allowing it to come on in worst case. Usually a little IR gets in there and some of it gets into the other one, but...
Yeah, and then what you end up with is some LEDs are running hot and bright and others are...
That's exactly right, yeah.
Or not even illuminated, and they start popping. So
yeah, cracking the die.
You almost always run LEDs because the manufacturing, the chips are so tiny in these. The manufacturing where they dice up the silicon die and turn it into little square pieces that they put on the lead frame and then wire bond.
Right.
The size of those can vary probably considerably, and so their internal they have a virtual resistor in series that's part of that diode VI curve, where it's like it's not, nothing, bam, suddenly it's conducting and forward biased, and it has to overcome that PN junction. And different LEDs have a different voltage where that happens. when I was a kid, and really until well into the mid 90s, blue LEDs didn't exist.
Same here. Yeah, most of my life, blue LEDs didn't exist. By the way, you're frozen, but your audio's coming in good, so keep talking.
Oh, well, that's good. So,
hey, you're back. You're back.
So, yeah, blue LEDs, and it's just different. It's different silicon. It's not silicon. Normal diode is silicon. You can have germanium diodes.
Germanium arsenide. Yep.
Yeah, LEDs, red and green LEDs are gallium arsenide, as you said. And to get the different color, they get different colors between infrared and green, and everything in between by tuning the fabrication process of the actual wafer. And then that was all they could do for so long. But then in the mid 90s, blue LEDs hit the market, and I remember they were not very bright. They were very dim at the time, and they were horrendously expensive. And they were made possible by this exotic new material, which is gallium nitride.
Nitride, yeah.
Yep. And gallium indium nitride.
Right.
They have different dopants, and they managed to dial in that manufacturing process to where now blue chips are actually the brightest. And you can get blue LEDs, you can get primary green. Green LEDs with gallium arsenide are actually more green-yellow, more like a chartreuse color, and they have a 2.1 volt forward voltage. Red LEDs with gallium arsenide are 1.8 to 2, but the blue chips are all 3 volts or higher. And so I was going to measure some of that today and show that. So you have to account for this. If you're mixing up different colors of LEDs, you can't just put red in parallel with blue or green or primary green, which is made with a blue dye chip and phosphors as well, just like white LEDs are. Right. So,
now, blue LEDs, my memory is they are basically what made CD players possible. That the reading head in a CD player to read the little moments on the disc needed the blue wavelength.
That's infrared for CD. So CDs came out. Sony came out with the first CD player in 1983. That was using gallium arsenide lasers. So blue made DVDs possible. So you could have
DVDs. That's it. Right. Sorry.
And Blu-ray. Actually, DVD also is infrared. It was Blu-ray that was made possible by blue LEDs. That's why they called it Blu-ray. Yes, you have much denser data because of the shorter wavelength.
Yeah, my first CD player was cost over $600, if I remember right. And it was in the mid 80s before we had blue LEDs, so I do stand corrected on that. But and then the rewritable discs were made possible by blue is also my memory. So Kevin asked IR. He wants to know what we mean when we say IR. And I means current and R means resistance. And so we're talking about the current versus resistance when we say an IR.
Oh, yeah, we should be clear about that and say current and resistance versus infrared. Because in today's discussion, it could be either, I guess.
Now, when we talk about putting LEDs in parallel, you will see LEDs that you can put in parallel, like for projects and whatnot. Those typically have a discrete resistor somewhere in the assembly. So you can put LEDs in parallel if there is an accompanying resistor with each of the LEDs, and that makes up the voltage drop. So in one resistor, you might get a volt drop, and the other one you get 0.9 volt drop. But that makes it so the LED can turn on at 2.1 and 2 volts respectively, for example. So by having a resistor isolate those forward voltage drops from each other, we can do LEDs in parallel, but it's twice the number of parts. So, all right, so show us what you're doing. You're making basically a fire hazard here out of a string of LEDs, basically, right?
Well, first I would just want to measure the characteristics of these because they didn't come with a data sheet. It was just a big old bag of warm white LEDs, right?
Right.
So I'll measure a few of them. And that's pretty bright, you can see. That's 19.5-ish milliamps, right?
Right.
And that's about the full brightness I would want. These could probably, at a pinch, I could push them to 30 milliamps. Most small LEDs, the general rule of thumb is you never drive them beyond about
Past
20.
15. I was going to say, I like 15, was what we used as a rule of thumb. They were designed for 19 to 20 in the old days. The, what was it, T1, one case, T1 and a quarter, or whatever that case was?
Yeah. And if you, if you look at LED data sheets, they typically say, nominal, absolute maximum ratings, they'll say 30 milliamps for forward. A lot of them 25, and they'll say nominal would be 20, but they'll give you a rated life of 50,000 hours. But then if you look at the fine print, they'll say it's 50,000 hours if you run it at 10 milliamps.
Right, right.
So LEDs, you generally need to drive them with a fixed current, and then you can vary pulse width to change brightness.
Right. So what we're really talking about is power dissipation, aren't we? I mean, there's a maximum current rating where you don't want to crack the die due to differential heating, but at the end of the day, it's really how much power is the die dissipating and the heat being removed.
Right. Right. And I want to measure the forward voltage drop because that does vary with loading.
Right.
So there's
a certain IR component to it.
Yeah, at that 19.5 milliamps, this one is 3.26 volts forward voltage drop. And again, so gallium nitride chips tend to have a 3 to 3.2 volt voltage drop. And actually, they did print that on the bag. If I look at the bag.
Did they? Oh, look at that.
VF 3 to 3.2.
How much did that bag cost you?
Oh, it was years ago. I don't remember. It was pretty cheap. I don't know, $10 or $20 or something for 1,000.
Right, right, cool.
So I like to measure a few of them and sort of get some idea of the distribution because they do vary. So this one is a 3.18 volt. See, it's a 3.23 volt.
And you're putting a VOM, a voltometer, directly across the LED and measuring the voltage that you see present in the LED. All right, we just lost Ben. So what Ben was doing, as I was just saying, is he was measuring the forward voltage drop by just putting a meter across the die and seeing what the voltage is. Hey, you're back. I was killing time there while you were gone.
Yeah. I'm sorry.
Not a problem.
That one's 3.19. Yeah, I hate the internet here. It sucks. I'm gonna.
We take the internet for granted. It's amazing that we are talking. We have people from all around the world are in the chat room, and the fact we can talk and see each other is just truly amazing.
It really is. So this one's up around 3.4 volts. Because that's outside of normal, I'm going to measure the current on that.
So, well, Kevin just asked diode check function. So the question is, I would rephrase that question and be, does the diode check function of the voltometer create enough voltage to turn on the blue LED or the white LED?
Well, let's find out. I don't think this meter will.
Yeah, let's find out.
Let's find out.
I'll bet it does, but it's not accurate. I'll bet the 3 volts of the batteries is close enough that it tickles it.
No, not even. It just says...
Not even? Okay.
This meter is old enough that the chip is probably designed to assume diodes only go to 0.7 VF.
0.7 of
reading
1
it as an
probably.
open
Yeah.
circuit.
Okay.
Yeah. So here's what I want to do. So I've got 37 LEDs at 3.2 volts. What's that? Do your mental math. 37 times 3.2. It's like... Okay.
Let's see if my calculator works. 37, enter. I use RPN, by the way. I'm an engineer. How many? It times 3.2. 118.
So I've got 118 drop. Now there's some interesting stuff we can do with that. So if you take United States or Canada or Mexico, North American mains voltage is 120 volts AC.
Right.
So but that's RMS. So if you rectify and filter that,
you get about 170. Yeah.
You get 170 volts DC basically, because that's the peak of the sine wave.
Right.
Or, if you're on the end of a long cable or something, it might drop down to 160.
Yeah, then it drops down based on load and stuff. Yeah, but the peak,
so,
1.414 times 132 volts will get you up there. So AC mains here, AC mains in U.S. is rated from 105 to 132. Turns out to be 120 plus 10 minus 15%, something like that.
Right.
So I used to design for 132 peak.
So here I've got this. This is the free microcap. This used to be a $4,000 or $5,000 package, by the way, and the authors of this product retired and made it a free download.
So what you're talking about, the software we see on the screen?
Yeah, it's a little quirky. It's got a very complicated UI that's very 1990s. But as far as SPICE circuit simulators go, it's fantastic. It competes right up there with PSpice.
Okay.
It even has a smoke test mode and things like that. But, I've put some generic white LED models on this design, 37 of them in series, right? So that gives us our VF and our LED characteristic response. And with 170 take away 118, you get about 50. You get 52 volts. No. Yeah, is that right? You get 50 or 40.
Say that again.
48. 170 take away 118
is 52 volts, right?
We get 52 volts peak on the drain of this MOSFET.
Right.
And it will never go above that unless these LEDs somehow turn into short circuits, which they won't.
Right.
Because we're going to be careful not to blow them up, right?
Right.
So the benefit of driving LEDs in a string is also that if you do need to power them off of a high voltage, you can still use somewhat lower voltage devices on the tail end.
Right.
So down here I can put a MOSFET and there'll be some inductance in here, so there could, if this ever turns off, if the updated version of this, once this works out, will be an opto isolator that allows me to drive it with some PWM, right? So basically this MOSFET could be just an 80 or 100 volt MOSFET for some safety margin. And because the voltage here is always like 50 volts-ish, I can pull up the base to turn it on straight from the drain, because this voltage will always be much higher than the base. I want to put a diode there, a Zener, to prevent the gate, from ever going beyond VGS maximum.
I was going to say, yeah.
But this technically that's not needed if I construct this circuit here. This is the current limit. So if I have a 33 ohm resistor here, this is a normal NPN transistor, just a popcorn component. Again, for margin, I'll probably use a BC 550 or something that can handle 60 or 80 volts on the collector. But with a 0.7 volt drop or 0.6 volt drop here, when it starts to bias on with the base, that means this sets the current through the source of the main MOSFET. So 33 ohms with 0.7 volts should give us a, what's that? What's the current?
Say that again. I was actually doing a different formula. I was doing I squared R.
Oh, well, but if you look at the base, because what happens is when the current through this resistor starts exceeding the current where the base of this goes above its turn-on voltage, which is 0.7 volts, this transistor turns on and pulls the gate low and starts turning this MOSFET off. So that's our feedback loop that creates the current limit.
Right. But with that said, wouldn't you get, if we're running the LEDs at 20 milliamps, the 20 milliamps will drain out through R1, right? Or is that not a ground on R1?
Yes, so R1 will dissipate some heat. That's our current sense resistor. For current sensing, you always have a resistor in series, and you always lose something. And a multimeter has a very sensitive current sense input, and instead of maybe a 1 ohm resistor, they'd even have a trace on the circuit board through which that's called your shunt. So they're just using the resistance of the circuit board trace, which is made to a certain tolerance, and measure the voltage across that tells you how much current's going through it.
Right.
In this case, we have a higher value resistor because that's going to set the current through our string to somewhere under 20 milliamps. So 0.7 volts at, what's the calculator there? 0.7 volts at 33 ohms.
0.7 enter 33 times and hang on.
Are you there, Bill?
Yeah.
Did I drop out
Can you
again?
hear me? No, can you hear me? Can you hear me? Hello?
I can now. Did I drop out for a second?
Maybe your audio did, because I think I was still transmitting. So what was the question? It was 0.7?
0.7
times
volts over 33 ohms.
23.1. Oh, over 33 ohms. Wait a minute. Now I'm just punching in.
0.7 divided by 33.
21 mils.
So that gives us 20 milliamps.
Right.
21 milliamps. But this will start to turn on at before 0.7 volts. So it'll actually, in practice, should be a little less. But we can measure it. We can measure it. If I get these parts out of the right bin, I could put them on this breadboard here. So anyway, let's do some DC analysis. So I've already run this before, but what I want to measure is I'm going to show the input voltage, which is 170 volts. I'm going to look at the voltage at the gate of the MOSFET, the current through the drain of the MOSFET. So that's the current through our LED string, and the power dissipation. I do care about that because I could end up, if I had fewer LEDs, I could have a very big voltage drop across this MOSFET for a fixed current. Increasing the voltage drop will increase the power dissipation, and I need to know, does it need to be heat sinked, or will I exceed its maximum ratings? So we'll go ahead and run that, and this is the result. This might be a little hard to see. Let's maximize, or that's even harder to see. I wonder if I can.
Yeah, I'm only seeing the page that shows the LEDs. I'm not seeing what you're moving around.
Oh, maybe because I stopped sharing. I'm sorry.
Yeah, I think you did say you stopped sharing at one point.
Am I sharing again? It should be sharing again.
I'm seeing the LED page.
I can see that in Skype too, but I've got the red border showing I'm screen sharing now.
All right, let me. Whoops, poop. Let me re-add you to the.
I'm going to stand up for a second, look closely at this because this is really small details here, and I want to make the lines thicker. So let me see, where can I format this? Edit styles. There. No, it's not that.
Yeah, so I'm not seeing your screen share in my menu here of NDI streams.
Width. I'm just going to increase the line width so they're a lot bolder.
And here you were worried if we had enough for a show today, and we're coming up on the top of the hour.
I can't believe it. But people will also want to see if I blow up myself or the strings on high voltage.
Right, right. Well, you mentioned breadboard, and I wouldn't put 170 volts through a breadboard either.
No, I really need to solder them together. I started trying to screen share again.
All right, let me look for the stream. I don't see the stream.
You have it showing that it's like static from when we started.
Right.
Maybe what if I drop off the call and join you again?
Yep,
or is
try
that
it.
too risky?
No, try
Okay,
it.
I'll be right back.
So we're playing with Skype here today, and let me see. Sorry for the delay, everybody. We're trying to reestablish Skype. So if somebody isn't on Skype, do they actually exist, or do they cease to exist until such a time as they're being measured? So this is an old physics question. Do people really exist when they're not on a Skype stream? So what I'm seeing right now is there's a poor network connection. We'll give them another minute here. Otherwise, we may end the show on that note here. And here we go.
Okay. Let's see if it works.
All right. Now try and share your screen. All right. I see something. And I don't see the screen share, unfortunately.
Wow.
Yeah.
That sucks.
So, yeah. Ben and I have been talking about alternatives to Skype. Okay, yeah, I see it changed. Let me see if I can pull that out of the mess here. Hey, there we go.
Yeah, that's it. And I had a chance to make the lines a bit thicker on the simulation graph. So this is a DC steady state analysis of.
Okay.
You can see the first one we've got. As input voltage, this is V1 volts, and I'm allowing it to vary from, where is it? That first graph I actually don't quite understand. It should be a straight line at 170, but whatever. We're not in transient analysis. We're in steady state. The next line down, the red one, we're looking at the gate voltage of the MOSFET as the input voltage. So actually, I could tell you if I go to DC limits, this is the DC analysis setup. So what I've actually got here is the x-axis is the DC input voltage. So as DC input rises, what happens to the y? Okay.
Right.
So as we vary, and we have a sweep of the V1 source. So that's not just fixed at 170. I'm sweeping it from 100 to 180 in 5 steps. So as we go from 100 volts at this end to 180, I should have switched those around. To me, that's kind of backwards. The output here also goes. Yeah, that graph makes no sense to me. I'll come back to that. I'll fix that up another time. The second graph is the gate voltage of the MOSFET, the pass device. So from 100 volts, the gate voltage goes to 0, which makes sense because our forward voltage drop of all those LEDs in series is 118 volts. So it's not until you start getting up over 118 that we start to see some current flow and therefore some gate turn on through this resistor to the gate of M1. And you can see it pretty much stays fixed almost entirely at about 4 volts, which happens to be what's needed. This is VGS, the voltage
VGS,
of
right,
the gate versus the source, which is this node here.
Right.
So that's basically regulating. So even above 100 and let's say that's, I don't know what's that. That's at about 122 volts, above about 128 volts. It's pretty much fixed to regulate the current, which is exactly what we expect. And our set current here is right around 21 milliamps at the maximum input voltage I've specified at 180. So then the power dissipation of the MOSFET, again, as it turns on, it starts to dissipate a bit more because it's getting more voltage drop across it with a more or less fixed current. And so up here, we can see we're dissipating at maximum voltage of 180 volts input DC constant. It's going to dissipate around 1.2 watts. So it might need some heat sinking. I am actually in the middle of designing a PCB for this along with a separate boost power supply so I can run the whole thing off an actual low voltage. So I can step 12 volts up to 140.
That'd be a great exercise, is to show how we take that wattage and turn it into a heat sink requirement. That's actually just using addition, subtraction, and a little multiplication. And yeah, that's right. Yep. Because we have a heat source, it's like a voltage source, and then we have thermal resistances, which are the loads between the die in the MOSFET and die to the case to the sink, and then sink to air. Yeah.
Yeah. Each of those is a thermal resistance in series, and we could say at steady state, that much power dissipation with these resistances to the ambient temperature, and this is our ambient temperature, means we're going to have this much temperature drop. It's just like calculating voltage drop in a string of resistance. Yeah. Yeah, that could be, maybe that could be the next time we stream. So, but at the outset, what I'm seeing here is that this will work. And the advantage, again, the advantage you have of driving LEDs in big long strings, if you have rectified mains power, is you get to use their forward voltage drops to your advantage in that you don't need a super expensive high voltage set of MOSFETs and resistors down here.
Right.
Some people might say that's risky, but I say, well, if you're concerned about all that, that's good. Put a fuse in series with it.
Yeah. Yeah, I did back when I was doing lights for a local rock group, I built a scanner, a thing that was meant to trigger the thyristors one after another. And it did kind of catch fire during one show, and I figured I had not used high enough voltages. I think I blew the base to collector voltage. Oh. There was yeah, I think I popped it not through the collector emitter, but through the base to collector voltage.
Yeah, yeah, because that's also an NP junction, and it only has so much. It only has so much
barrier to it before it pops. Yeah.
Yeah, and you can end up, it'll arc inside, and then you end up with a little short circuit, and then that grows to a big short circuit very quickly, and then the whole thing goes up.
Right. It was actually pretty comical because I'd made a row of LEDs to show the scanner. The smoke was coming out of the hole. You know, I had my own chassis I'd built. The smoke was coming out of the row of holes, so it made a ribbon of smoke. And so as a joke, I went and got a fire extinguisher and set it down next to the board. The band kept playing. They didn't know anything's going on, and everybody's kind of giggling that I have smoke pouring out of my board. I figured at that point the scanner part's already fried, but the thyristors kept kicking. So, you know, it's... And that's what I was known for my local rock group was, you know, I had a thyristor-based light board with a organ keyboard would trigger each string of lights, but then I had hand wound my own filters so that I didn't have all this hum and buzz getting into the amplifiers. And then I also carried a 50-foot extension cord, and I would make sure I plugged into a different circuit, sometimes into the neighboring circuit to isolate the...
I'm so glad everything's LED now too, because I did lighting when I was in my college years, and I was always popping breakers in wherever I went. There was never enough power because we had par 64 cans,
right?
And so the smaller gigs we'd have to downsize to par 56s. But even a par 56, one light bulb was 300 watts. A par 64, one light bulb was 1,000 typically, unless it was a narrow beam in which they were only 500. And it was hard to have more than 8 lights in some places because you'd just constantly be fighting their power limitations.
Right, right.
The best concerts I did were outdoor, and we would always have a 200 kilowatt generator behind the stage. Right. You know, this truck would come in and dump this thing. It's a big white box, all sound insulated and everything. We put a ground stake in and wire it to the earth, and then off we would go. And it was our mission to get the needles all the way up to maximum if we could.
Right.
At the highlight of the gig, we'd have someone at the crescendo moment with the loudest drums and all the lights on. We'd have someone there with a camera waiting to take a picture of the needle getting to its maximum.
Yeah. The biggest show I ever did, we rented the lights for, and for power, I actually opened the big breaker box of the whole National Guard Armory and got in there with clamps. And I remember my colonel, no, he wasn't the colonel, he was a lieutenant, standing there watching me do it. And he knew me from being in the Guard. So here I am in long hair, because normally in the Guard, I had a short-haired wig I would wear, and this is the 70s. And so I'm sitting there clamping on live current and voltage and looking like I know what I was doing. And yeah, I didn't die, and we never blew a breaker. So
very cool, very cool.
So hey, we should call it there. It's 8 minutes after the hour. I really like to think the topic of, you know, hey, so we know the power dissipation needs of, what did we say the FET needed for power dissipation, like 1.8 watts, something like that.
The maximum dissipation is 1.2 at
1.2 watt
at peak line voltage. Yeah.
All right. Yeah, so that should be straightforward to say, well, 1.2 watts, how do we keep the junction temperature below 125 degrees C is a reasonable value to keep your junction temperature at. or below. You can make it less if you want, but that's what I shoot for.
So I feel like I owe everyone some lights.
Yeah, let's do it. Let's do it.
And some danger.
You watch the whole show just comes to an end with just one of those sniglets like they used to be on the TVs in the old days.
Well, here's the thing: are we next week on Friday is Christmas
Eve.
So I don't know if you're open to streaming Christmas Eve or what we'll all be doing. I suspect we'll be going to different parties and eating too much bad food. So the question is, do we stream next week or
even the week after?
I think I think as an incentive, if you're seeing this, you need to get on our Discord. Go to Coriolis-effect.com, and there's a link at the top to join our Discord.
Also a link at the top of the chat for YouTube this time.
Yeah.
So the very top first comment.
So I think what I need to do is finish stuffing the rest of this. All the LEDs, I have to be careful the orientation to make sure none of them are reversed so that it actually works. I'll get all of that. The other thing I wanted to discuss, this is just a tip for anyone watching. If you need a mains power source that's isolated, you could go out and buy an expensive isolation transformer, and every good workbench, especially anyone doing power supply design like I do occasionally, I have a Variac and I have an isolation transformer that only spits out 100 volts, but that plus the Variac can give me some of what I need. But another really easy way to do it that's really cool, get an uninterruptible power supply, and you can pick them up cheap secondhand off eBay.
Right, they're not sine waves typically, they are square-ish, just to be clear about that.
Some of them are.
You can get sine wave ones, but cheap ones aren't. Yeah.
Yeah. I have an APC 1800 watt, I think it is. It's modified sine wave, so it's squarish. But it's a cheap, easy source of AC 120 volts that I could put on my workbench here and have it unplugged and just running from the battery, and it enables me to work with isolated high voltage, so I don't have to worry about getting hooked up with ground or anything.
So here's the question I'll leave us with here, or discuss real quick. If you got one of the LEDs backwards, right, the full 170 volts would appear across that LED because it's not in conduction. True enough?
Because all the other LEDs are still pointing
not
the
in
other
conduction
way.
either. Right.
And so those LEDs still have their VF of 3 volts all adding up. If just one of them in the middle somewhere was back to front, I believe it would have no trouble, because none of them would be effectively like being open circuited. Right.
So where I was headed with the question is, what is the reverse voltage breakdown of the LED? Is it enough to handle,
Yeah,
because we've been talking about the forwards.
That's a big difference between LEDs and normal diodes. They usually have a very low reverse breakdown voltage rating.
Right.
And so you do have to be careful. Yeah. Sometimes, like for even a 2.1 volt forward bias LED, will only have a rating on the data sheet of maximum reverse voltage of 5 volts.
Okay.
So yeah, we do have to watch that.
Right.
So I am going to be very careful how I insert them into the string. I'm going to build the current source. And
you
I'll
should get one of those automatic AEDs, one of the automatic defibrillators, and hang it on the wall behind you as a joke,
Yeah, well, I'm here on my own, and no one else is here or knows I'm here except for some family members. So an AED won't do me much good.
Right. Still need somebody to operate it. Yeah.
But I'm thinking I'll do a quick follow-up video and record the whole thing and make some measurements.
Throw it up on Discord. Yeah.
And post it to Discord. Just so it can be ready before the actual holiday that the lights are all about. So.
Right. So, all right. So maybe we'll see everybody here next week. Maybe not. We don't know yet. But hang out in Discord, and we will talk about it there, maybe.
Yeah. Yep.
So,
Good
excellent.
to see you, Bill.
Good seeing you again. And we'll see you, if not next week or the week after that. But we'll definitely be back here at some point.
And
all right.
In any case, have wonderful holidays, everybody. And,
everybody, have a safe holiday.
Yeah, be safe, and if you're not being safe, do something really fun like snowboarding. That's not exactly safe, but it's super fun. Or messing around.
Play high voltage LEDs. Yes.
Whatever
right.
you do, don't hook yourself up or do anything silly.
Right. No making your own AEDs. Right.
Yeah. Bill and I are trained professionals. We've been very experienced with high voltage and electronics for a long, long time. So, just for the sake of YouTube and kids out there,
don't do this at home.
Don't do this at home unless you've had the training we've had.
Or do it as a software simulation.
Yeah, definitely. Go find MacroCap. You can download it for free. You can create the same model, and you can actually run smoke tests. It'll actually tell you, if you run the smoke analysis, if you exceed the ratings of a given component in the design. It'll say, hey, this component's going to blow up. That's why they call it the smoke.
Right.
Smoke.
And a real good simulation will tell you the blast radius and number of survivors. So it's... All right. Totally. You have a good one. Take care, everybody, and have a safe and merry Christmas, happy holidays, and be safe.